The Event-Driven Blueprint, Building Modern, Agile, and Resilient Systems. Chapter 1, The Pulse of Modern Systems. What is event-driven architecture? Imagine a bustling city that operates in perfect, silent harmony. Traffic lights change precisely when cars are ready, ambulances clear paths as soon as they sound their sirens, and every door opens just as someone approaches. This isn't magic. It's a system where every component reacts instantly and independently to crucial information. An event that signals something significant has just happened. In the world of software, our systems are often far from this ideal. For decades, much of our digital infrastructure has operated like a series of telephone calls. When one part of a system needs something from another, it makes a direct call, waits for a response, and only then proceeds. Think of it like ordering a custom meal. You tell the chef your order, the chef tells the waiter tells the kitchen, and everyone waits until the dish is ready. This request and response dance works, but it can be slow, fragile, and difficult to scale. If one person in the chain is busy, or worse, unavailable, everyone else is stuck waiting. This is where the concept of event-driven architecture, or EDA, steps in as a profound shift. Instead of making direct calls and waiting, components in an event-driven system communicate by declaring something just happened. They don't care who hears it, or what they do with the information. They simply announce a fact and then move on. It's less like a direct phone call and more like a broadcast announcement or a newspaper headline. At its heart, an event is simply a digital fact. It's an immutable record that something significant occurred within your system. Crucially, it's always in the past tense: a payment processed event, an order placed event, a user registered event. It's not an instruction to do something. It's a declaration that something has been done. This subtle but powerful distinction is the bedrock of EDA. Consider a simple, real-world example: an old-fashioned mail-order catalog system versus a modern online retailer. In the old mail-order system, you'd call a customer service representative. They would request an item from inventory, wait for confirmation, then request your credit card to be charged, wait for approval, and finally request the shipping department to send your package. Each step was a direct, sequential interaction. If the inventory department was on lunch break, your order sat in limbo. Now, imagine a modern online retailer built with event-driven architecture. When you click Place Order, the system instantly declares an order-placed event. This single event is then simultaneously made available to various listeners. The payment processing system hears the order-placed event and immediately initiates the charge. The inventory system also hears the order-placed event and updates its stock. The warehousing system hears the order-placed event and prepares the package for shipment. The marketing system hears the order-placed event and sends you a confirmation email. Notice something vital here: none of these systems are waiting for another. The order processing system doesn't directly tell the inventory system to deduct stock. It just announces the order-placed event. The payment system doesn't wait for the warehouse to confirm shipment before charging your card. They all react to the same fundamental fact, independently and often concurrently. In EDA, the component that generates these events is known as the event producer or event source. The components that listen for and react to these events are called event consumers or event listeners. The crucial link between them is an event broker, which acts as a central hub, ensuring events are reliably delivered from producers to interested consumers. Much like a post office ensures mail gets to the right addresses. This asynchronous, decoupled way of operating offers tremendous advantages. By letting systems declare facts and react independently, we inherently build in greater agility, making it easier to add new features or modify existing ones without disturbing the entire structure. Systems become more scalable, able to handle massive volumes of activity as each component can be scaled up or down based on its own workload, rather than being limited by the slowest link in a chain. And critically, they become more resilient, as the failure of one consuming system doesn't necessarily halt the entire operation. The events might simply queue up until the system recovers, or other systems can continue their work unaffected. While the term event-driven architecture might sound like a modern innovation, its roots actually stretch back decades. building on concepts like message queues, enterprise application integration, EAI, and publish-subscribe patterns. What's new is the widespread adoption, the maturity of the underlying technologies, and the recognition of its power in building the robust, responsive, and ever-evolving digital platforms that power our world today. From real-time financial trading to streaming media services and interconnected smart devices, events are the silent, constant pulse keeping countless modern systems alive and thriving. To truly master this architectural style, however, we must first understand its core vocabulary. What exactly is the difference between an event and a message? How do commands fit into this picture? And how does the communication truly flow beneath the surface? In the next chapter, we'll demystify these foundational terms, providing you with the precise language needed to navigate the event-driven landscape. Chapter 2. The core vocabulary, events, messages, and the communication flow. In our exploration of event-driven architecture, we quickly encountered the term event as a central concept. But to truly understand and harness the power of EDA, we need to distinguish it from similar concepts and establish a precise vocabulary. What is an event, really? How does it differ from a message or a command? And how do these distinct pieces of information travel through a system? Let's dissect these terms with precision, as their accurate understanding is fundamental to designing robust event-driven systems. The event. A statement of fact. As introduced, an event is an immutable past-tense statement of fact about something that occurred in a system. Think of it like a news headline: stock market crashes, new law passed, local store opens. These are declarations of things that have already happened. Key characteristics of an event: immutable. Once an event occurs and is recorded, it cannot be changed. It's a historical record. Past tense always describes something that has happened. Examples: order placed, user registered, product viewed, payment failed. Factual: it conveys objective information about a state change without implying any specific action that should be taken. Contains data. An event typically carries data relevant to the occurrence. For a user-registered event, this might include the user's ID, a timestamp, and how they registered, e.g., via email, social media. It does not include sensitive personal data directly. Rather, it refers to an identifier that another service can use to retrieve that data if authorized. The beauty of events lies in their simplicity and objectivity. A service that emits an order-placed event doesn't care if that order will be picked, packed, shipped, or recorded for analytics. It simply announces that an order was placed, providing the necessary context. The message. A broader category. While all events can be considered messages, not all messages are events. A message is a broader, more generic term for a discrete unit of communication sent between components or systems. It's like a piece of mail. Messages can carry different intents. Events, as we've discussed, notifications of something that has occurred. Commands, an instruction to another service to do something. Queries, a request for information from another service. Imagine sending a message. If the message says, "I closed the deal," that's an event. If it says, "Close the deal," that's a command. If it says, "What's the status of the deal?" that's a query. In this book, when we discuss messages in the context of event-driven systems, we're very often referring to events traveling through the system. The command, an imperative instruction. A command is an instruction or a request for a specific action to be performed by a particular recipient. Unlike an event, a command is imperative and future-oriented. It's like saying, "Ship this package immediately," or "process this payment." Characteristics of a command. Imperative. It tells a service what to do. Future tense, present tense. It asks for an action to be taken now or in the future. Targeted. Typically directed at a specific service or component that is responsible for executing that action. There's an expectation of a response, success, or failure. Mutable potentially. While the command itself doesn't change, its execution might lead to a different outcome or state. In an event-driven system, a service might consume an event, e.g., order placed, and, as a result of processing it, issue a command to another service, e.g., charge customer command to a payment service. The payment service would then process that command and, upon success, emit another event, payment processed. The query, a request for information, A query is a request for information from a service. It's typically synchronous. The requesting service sends a query and waits for a response containing the requested data. While EDA focuses on asynchronous communication, queries still exist, often used for reading data from specialized data stores that reflect the current state of the system derived from past events. For instance, a user interface might query a customer profile service to display a user's details. The flow, producers, consumers, and the broker. Understanding these distinctions helps us visualize the path information takes within an event-driven system. This path involves three primary architectural roles. Event producer, source. This is any component or system that generates and publishes events. It's the origin point of a factual declaration. A web service might produce a user-logged-in event. A database might produce a record-updated event, or an IoT device might produce a temperature reading event. The producer emits an event and typically doesn't care who receives it or what they do with it. Its job is done once the event is successfully sent to the event broker. Event consumer, listener subscriber. This is any component or system that listens for and reacts to events of interest. Consumers subscribe to specific types of events from the event broker. When an event they are interested in arrives, they retrieve it and perform some action. For instance, a shipping service might consume order-placed events to initiate package preparation, while an analytics service might consume the same order-placed events to update sales dashboards. A single event can be consumed by multiple, independent consumers. Event broker, bus channel stream. This is the central nervous system of an event-driven architecture. The event broker is responsible for receiving events from producers and reliably delivering them to all interested consumers. It decouples producers from consumers, meaning producers don't need to know anything about the consumers, and consumers don't need to know anything about the producers. This intermediary role is crucial for scalability, reliability, and flexibility. How does the event broker manage this flow? Two common concepts come into play. Queues. A queue is a messaging channel that ensures each message, or event, is processed by only one consumer. It typically operates on a first-in, first-out FIFO basis. Imagine a single line at a checkout counter. Each customer message is served by just one cashier consumer. Queues are ideal for tasks that need to be processed once, like transferring money or sending a single notification. If multiple instances of a consumer are listening to the same queue, they act as competitors, each picking up a different message. Topics or streams. A topic is a channel where an event published to it can be received by multiple consumers. It operates on a publish-subscribe model. Think of a news broadcast. Many individuals can tune in and receive the same transmission. Topics are powerful for broadcasting events to multiple services that need to react independently to the same occurrence. For example, an order-placed event could be published to a topic, and the payment service, inventory service, and marketing service could all subscribe to that same topic and receive their own copy of the event. The flow within an EDA system goes something like this. Producer emits an event. A service performs an action, e.g., changes a user's status, and emits an event, user status changed, to the event broker regarding this occurrence. Event stored rooted by broker. The event broker receives the user status changed event and stores it in a topic or queue, making it available. Consumers receive the event. Any consumer service that has subscribed to user status changed events receives a copy of this event from the broker. Consumers process the event. Each consumer independently processes the event according to its own business logic. For example, one consumer might update a user profile database, another might send an email notification, and a third might trigger an analytics update. New events commands queries, optional. As a result of processing an event, a consumer might in turn become a producer, emitting new events, email sent, issuing commands to other services, adjust loyalty points, or performing queries to fetch additional data. This asynchronous, indirect communication through an event broker is what grants event-driven architectures their remarkable flexibility and power. By breaking down tight dependencies and enabling independent reaction to factual declarations, we open the door to systems that are not just robust and scalable, but also incredibly agile and adaptable to an ever-changing digital landscape. In the next chapter, we'll dive deeper into these profound benefits, exploring why more and more organizations are choosing to embrace the event. Chapter 3: Why Embrace the Event? Unlocking Agility, Scalability, and Resilience. Having explored the fundamental components of event-driven architecture and understood what an event truly is, the next crucial question is, why should any organization bother with this paradigm shift? What inherent value does moving from a traditional request and response model to an event-driven approach offer? The answer lies in EDA's profound ability to address some of the most persistent and challenging problems faced by modern software systems. Rigidity, fragility, inability to scale under pressure, and difficulty adapting to new business demands. By embracing the event, organizations can unlock unprecedented levels of agility, scalability, and resilience. Let's delve into these core benefits. 1. Decoupling. Breaking free from tight dependencies. In traditional architectures, especially large monolithic applications or microservices that rely heavily on direct API calls, components are often tightly interdependent. If Service A needs data from Service B, Service A calls Service B. This creates a direct, often brittle, dependency. A change in Service B might inadvertently break Service A, or a failure in Service B could halt Service A entirely. This is like trying to untangle a ball of yarn where every thread is knotted to every other. How EDA helps. Event-driven systems promote loose coupling. The producer of an event, e.g., an order service, doesn't know or care who consumes its events. It simply publishes the fact that an order was placed. The consumer's, e.g., payment service, inventory service, shipping service, react independently to this event. Scenario: imagine an e-commerce system. In a tightly coupled setup, the order service might call the payment service directly, then wait for its response, then call the inventory service, and so on. If the payment service is down or slow, the order service slows down or fails, impacting the entire order placement process. In an event-driven system, the order service fires an order-placed event and immediately moves on. The payment service and inventory service pick up this event asynchronously. If the payment service is temporarily unavailable, the order service isn't blocked. Orders can still be accepted, and the payment can be processed later or retried by the payment service when it recovers. This vastly improves the system's overall robustness. 2. Scalability. Handling peaks with grace. Modern systems often experience unpredictable fluctuations in workload. A social media platform might see a massive surge during a viral news event, or an online retailer might be swamped during holiday sales. Traditional architectures often struggle with these peak loads, leading to slow performance or outright crashes, because every component directly involved in a synchronous interaction must scale equally. How EDA helps. Event brokers, with their built-in queues and topics, act as buffers. When a sudden burst of events occurs, the broker can absorb and store them temporarily. Consumers can then process these events at their own pace. If the incoming event rate consistently exceeds the processing capacity, you simply add more instances of the consumer service, horizontal scaling. Each new instance picks up messages from the queue or topic, distributing the processing load. Scenario: consider a fitness tracking application with millions of users. During peak morning and evening workout times, there's a surge of location updated, heart rate measured, and workout completed events. Instead of a single backend service trying to keep up with direct requests from every user's app, these events are streamed into topics. Dedicated services for calorie calculation, gamification leaderboards, and historical analytics can each consume these events. As the event volume spikes, the calorie calculation service can automatically spin up new instances, allowing it to keep processing events without affecting the leaderboard service, which might not be experiencing the same load increase. This independent scaling ensures that the system remains responsive even under extreme pressure. 3. Resilience and fault tolerance. Building antifragile systems. Failures are inevitable in complex distributed systems. A database might go down, a network connection might drop, or a server might crash. In tightly coupled systems, a single point of failure can trigger a cascade, bringing down large parts of the application or even the entire system. How EDA helps. The asynchronous and decoupled nature of EDA inherently builds resilience. Since producers don't wait for consumers, they are protected from consumer failures. If a consumer fails, the event broker typically retains the events, allowing the consumer to restart and resume processing where it left off, preventing data loss. Moreover, if one part of the system experiences an issue, other parts can often continue to function, providing at least degraded service rather than a complete outage. Scenario: think about an online banking system. A withdrawal requested event is produced. Even if the service responsible for updating the customer's transaction history briefly goes offline due to a deployment error, the withdrawal requested event is safely stored in the event broker. The core withdrawal process can proceed, funds deducted from account, etc. Once the transaction history service comes back online, it can pick up the pending events and process them, ensuring all records are eventually consistent. The system as a whole avoided a complete freeze simply because one downstream service had a temporary glitch. For agility and evolvability, adapting with ease. Business requirements change constantly. Adding a new feature, integrating with a new third-party service, or introducing a new compliance rule can be a monumental task in monolithic or brittle microservice architectures, often requiring extensive code changes and retesting across multiple interdependent components. How EDA helps. EDA dramatically improves agility because new functionality can often be added by simply creating a new consumer that subscribes to existing events. You don't need to modify the producers or existing consumers. This is like adding a new app to your smartphone. You don't need to redesign the phone's operating system or rewrite existing apps. Scenario: let's revisit our e-commerce platform. The business decides to introduce a new loyalty program that gives points for every purchase. In an event-driven system, a new loyalty program service can be created. This service simply subscribes to the existing order placed and payment processed events. It then calculates and awards loyalty points based on the data in these events. The order service and payment service don't need any modification. This independent development and deployment allow the business to react quickly to market demands without fear of breaking existing, stable functionality. 5. Auditing, replayability, and event sourcing. A factual history. Because events are immutable facts that represent something that happened. Collectively, they form a chronological, indelible log of every significant change in your system. This event log can be leveraged for powerful capabilities that are difficult to achieve in traditional systems. How EDA helps. Auditing provides a precise and undeniable record of all activities, invaluable for compliance, security, and debugging. Time travel replayability. The sequence of events can be replayed to reconstruct the state of a system at any past point in time. This is particularly useful for debugging complex scenarios or for creating new views of historical data. Think of it like a never-ending video recording of your system's life. Event sourcing, advanced. A powerful pattern where the definitive truth of the system's state is not stored in a traditional database table, but as a sequence of events. The current state is simply a projection derived by replaying these events. This opens doors to advanced data consistency models and historical analysis. Scenario: a customer calls support about a missing refund. In a traditional system, a support agent might see a refund status field as processed, but have no idea how it got that way. With an event log, they can unfold the sequence. Refund initiated event, then refund processed by payment provider event, then refund failed event due to an invalid account, followed by refund retry scheduled, and finally refund successful. This clear, immutable history vastly simplifies debugging, enables precise analysis, and builds trust. 6. Real-time analytics and business intelligence, instant insights. In traditional batch processing, business intelligence reports often lag behind real-world events by hours or even days. Decisions are made on stale data. How EDA helps. Events provide immediate, real-time data points. As events flow through the system, they can be captured, transformed, and used to update dashboards, trigger alerts, or feed machine learning models instantaneously. Scenario: a sales manager wants to see real-time sales trends during a flash sale. As payment processed events occur, they can instantly update a dashboard showing sales volume, revenue, and popular products by the minute. This immediate feedback allows the sales team to adjust promotions or inventory on the fly. Similarly, security teams can react to login attempt failed events in real time to detect and mitigate potential brute force attacks far more quickly than waiting for daily log analysis. The shift to an event-driven paradigm is not without its complexities, which we will explore in later chapters. However, the benefits of building systems that are inherently more agile, scalable, and resilient are compelling arguments for its adoption. By thinking in terms of what happened, rather than what should I ask for, we move towards building systems that are more aligned with the dynamic, unpredictable nature of the real world they intend to model and serve. Chapter 4. Navigating the Currents, Common Challenges and Pitfalls in EDA. In the previous chapter, we painted a compelling picture of event-driven architecture's many virtues. Its ability to foster agility, enhance scalability, and build resilient systems. However, like any powerful tool or sophisticated architectural style, EDA comes with its own set of complexities and potential pitfalls. It's crucial to approach it with a clear understanding of these challenges, as foresight can prevent costly missteps and ensure that the benefits genuinely outweigh the added effort. No architectural approach is a silver bullet, and EDA is no exception. While it solves many problems inherent in traditional systems, it introduces new considerations that demand a shift in mindset, tooling, and operational practices. Let's explore some of the common currents you'll need to navigate when embarking on your event-driven journey. 1. Increased complexity, the distributed nature of things. Perhaps the most significant challenge of EDA is the inherent increase in system complexity. When you separate components and have them communicate asynchronously through events, you lose the simplicity of a direct function call or a single logical flow of execution. Debugging and tracing. In a traditional request-response system, if a user clicks a button and an error occurs, you can often trace a single path through the code, inspecting variables along a call stack. In an event-driven system, a user action might trigger an event, which is then picked up by one service, which might emit another event, leading to another service, and so on. There's no single call stack across the entire interaction. This distributed nature makes it significantly harder to trace the flow of data and debug issues across multiple independent services. Specialized tools for distributed tracing become essential to visualize how an event propagates through the system. State management. With services operating independently, ensuring a consistent view of data across multiple systems can be tricky. While eventual consistency is a powerful concept, which we'll discuss shortly, it means you can't always assume all parts of your system instantly reflect the very latest information. Orchestration versus choreography. EDA strongly favors choreography, where services react autonomously to events. For simple workflows, this is great. But for complex, multi-step business processes that require strict ordering or compensation logic, rolling back actions if a later step fails, pure choreography might become unwieldy. Sometimes, a degree of orchestration, a central coordinator guiding the workflow, might still be necessary, adding another layer of complexity to design. 2. Event schema management and evolution. The backward compatibility headache. Events are contracts. They describe specific data structures that producers emit and consumers expect. What happens when you need to change an event structure, add a new field, rename an old one, or remove something entirely? Backward compatibility. If a producer changes an order-placed event to include a new field, e.g., delivery instructions, older consumer services might not know how to handle it or might simply ignore it. More dangerously, if an existing field is renamed or removed, older consumers might break because they expect that field to be present. Forward compatibility. Newer consumer services might be deployed that expect next-generation event structures. How do they deal with older events still being processed? Versioning strategies. Managing event schema evolution requires careful planning and often involves versioning strategies, e.g., order placed v1, order placed v2, and robust serialization formats that support schema changes gracefully. Without proper governance, event schemas can quickly become a tangled mess, leading to constant refactoring or broken integrations. 3. Eventual consistency. The mind shift to eventually true. One of the most fundamental shifts in thinking required by EDA is embracing eventual consistency. In a traditional, single database application, most data is immediately consistent. Once you save a change, everyone sees it. In a distributed event-driven system, when an event occurs, it takes time for all the interested consumers to process it and update their own local data stores. User experience implications. This delay, however small, can sometimes be visible to users. For instance, a user might place an order, but for a split second, their shopping cart still shows the item, or a product count isn't immediately updated. While often acceptable, it requires careful design to ensure a smooth user experience and to manage user expectations. Data integrity challenges. While eventual consistency is robust, it means you must design systems that can tolerate temporary inconsistencies. If a series of events leads to a decision being made based on slightly outdated data, how does the system recover or reconcile? This demands a deeper understanding of transactional boundaries in a distributed world, often requiring compensatory actions or idempotent operations. 4. Idempotency and deduplication. Processing events exactly once. Due to the nature of distributed systems, events might occasionally be delivered more than once. This can happen due to network glitches, consumer crashes and restarts, or retry mechanisms. Idempotency. A consumer must be idempotent, meaning that processing the same event multiple times produces the same result as processing it just once. If processing an event charge customer twice leads to the customer being charged twice, then your system isn't idempotent. This often requires careful tracking of processed events or designing operations that inherently produce the same result regardless of how many times they are applied, e.g., setting a value rather than incrementing it. Deduplication. Strategies are needed to prevent processing duplicate events where idempotency isn't easily achievable. This might involve consumers storing unique identifiers for processed events to check for duplicates before acting. 5. Event ordering guarantees. When sequence matters. In some scenarios, the order in which events are processed is absolutely critical. For example, a funds deposited event followed by a funds withdrawn event produces a different outcome than funds withdrawn followed by funds deposited. Challenges with distributed ordering. While most event brokers guarantee ordering within a single partition or for messages sent to a single topic key, global ordering across all events in a system is incredibly difficult to achieve and often unnecessary. Designing for ordering. When ordering is critical for a particular entity, e.g., a bank account, services often process all events related to that entity, e.g., account ID XYZ, through a single channel or partition to guarantee sequence. This requires careful design to define boundaries where strict ordering matters and where it doesn't. 6. Operational overhead and infrastructure management. Adopting EDA often means introducing significant new infrastructure components, namely robust event brokers like Apache Kafka, RabbitMQ, or cloud-managed services. Complexity of operations. Managing and operating these brokers at scale requires specialized expertise. You need to monitor their health, understand their configuration, handle upgrades, and troubleshoot performance bottlenecks. Resource consumption. Event brokers can consume significant computing resources, memory, and storage, leading to increased infrastructure costs. Monitoring and alerting. Setting up comprehensive monitoring for event streams, tracking message rates, consumer lag, error queues, and dead letter queues is crucial for understanding system health and reacting to problems quickly. 7. The cultural shift. Thinking in events. Perhaps the most underestimated challenge of adopting EDA is the cultural and conceptual shift it demands from development teams. Developers and architects accustomed to synchronous, request-response paradigms need to learn to think asynchronously, reactively, and in terms of facts. What happened? Rather than direct commands, do this. Designing events. Deciding what constitutes a meaningful event and what data it should carry is an art as much as a science. Too many granular events can lead to noisy systems, too few, and you lose valuable context. Distributed ownership. Teams often own isolated services, but events flow across these boundaries. This requires strong cross-team collaboration and clear contracts for event schemas. Testing. As mentioned earlier, testing in a distributed, asynchronous environment is fundamentally different. It requires new testing strategies and tools. Successfully navigating these currents requires thoughtful planning, the right tools, and a willingness to embrace new ways of thinking and working. It's a journey, not a destination, but one that offers profound rewards for those who master its complexities. In the next chapter, we will shift our focus from challenges to solutions, exploring the foundational patterns that help us structure and manage these event flows effectively. Chapter 5, Building Blocks of Flow, Essential Event-Driven Patterns. In the previous chapter, we navigated the challenging currents of event-driven architecture, acknowledging that its power comes with increased complexity. Now, we turn our attention to the solutions, the proven architectural patterns that serve as the building blocks for managing this complexity and effectively harnessing the flow of events. These patterns are like the established engineering principles that allow bridge builders to span vast chasms or city planners to manage complex traffic flows. They provide a common language and a set of battle-tested approaches to tackle recurring design problems in event-driven systems, moving from abstract concepts to concrete implementations. Let's explore some of the most essential event-driven patterns. 1. Publish-Subscribe, PubSub, the broadcasting hub. This is the most fundamental pattern in EDA and forms its very backbone. We've already touched upon it, but it bears repeating its precise role. What it is. In PubSub, event producers, publishers, send events to a central event broker without knowing anything about who will receive them. Event consumers, subscribers, register their interest in specific types of events with the broker. When an event matching their interest is published, the broker delivers a copy of that event to each interested subscriber. Analogy. Think of a newspaper or a news channel. The journalists, publishers, write stories events and send them to the news agency broker. Many diverse readers or viewers, subscribers, then consume the news stories they find relevant. The journalist doesn't need to know each viewer personally or send them a specific message. Why it's useful. PubSub is the ultimate enabler of decoupling. It allows services to evolve independently, as changes in one service, e.g., adding a new consumer, do not require changes in other services, producers. It also supports massive scalability, as many consumers can read from the same stream of events concurrently. 2. Event sourcing, the unfolding ledger of truth. This pattern shifts our understanding of how system state is recorded. Instead of merely storing the current state of an entity, like a customer account's balance, event sourcing stores every change to that entity as an immutable sequence of events. What it is. The definitive state of an application object, e.g., an order, a customer account, is not stored directly in a database table. Instead, it is represented as a chronological sequence of all the events that have affected it. To reconstruct the current state, you replay all relevant events from the beginning. Analogy, imagine a financial accounting ledger. You don't just store the current bank balance. You store every single transaction, deposit, withdrawal, transfer that contributed to that balance. To find the current balance, you sum up all the transactions. To see the balance at a specific point in the past, you sum up transactions up to that date. Why it's useful. Complete Audit Trail provides an indisputable, fine-grained history of everything that ever happened to an entity, invaluable for debugging, compliance, and dispute resolution. Time travel debugging. You can go back in time and reconstruct an entity's state at any given moment, which is incredibly powerful for diagnosing issues. Historical analysis. Enables complex analytical queries against historical data that would be difficult to perform if only the current state was stored. Enables CQRS. Event sourcing naturally pairs with the command query responsibility segregation, CQRS pattern. 3. Command Query Responsibility Segregation, CQRS. Optimizing for reads and writes. CQRS is often used in conjunction with event sourcing, but it can also be used independently. It's about separating the way you update data from the way you read data. What it is. Instead of using one monolithic data model and persistence mechanism for both writes, commands, and reads queries, CQRS segregates them. The command-side write model focuses on processing actions and typically involves complex business logic. It usually processes commands and, as a result, emits events, especially if using event sourcing. The query-side read model focuses on efficiently serving data for various displays or reports. It listens to events from the command side and updates one or more specialized, optimized read-only data stores as needed. Analogy: think of a fast food restaurant. There's a tightly controlled system for taking new orders and processing payments, the write model, ensuring correct inventory and transactions. Separately, there might be large, clear menu boards optimized for customers to quickly browse available items and their prices, the read model. The menu boards update when a new item is added or prices change, but they don't directly handle orders. Why it's useful? Independent optimization. You can optimize the write and read paths independently for performance and scalability. For example, the write model might be highly normalized for transactional integrity, while the read model might be denormalized or graph-based for fast queries. Flexibility allows different teams to work on the write and read models simultaneously without stepping on each other's toes. Coping with complexity reduces complexity in some parts of the system by allowing each model to be tailored to its specific purpose. Consideration introduces eventual consistency as the read model updates asynchronously from the write model. 4 sagas, distributed transactions, orchestrating complex workflows. While individual services in an EDA are decoupled, many real-world business processes involve multiple steps across different services that need to complete successfully or be fully undone. This is where sagas come in. What it is. A saga is a sequence of local transactions where each local transaction is executed by a different service. Each step in the saga performs its local transaction and publishes an event, which then triggers the next step in the saga. If a step fails, the saga executes a series of compensating transactions to undo the effects of previously completed steps, ensuring eventual consistency. Analogy: booking a multi-legged trip. Book flight, local transaction. If successful, publish flight booked event. Hotel booking service receives flight booked event books hotel. If successful, publish hotel booked event. Rental car service receives hotel booked event books car. If successful, publish car booked event. If the rental car booking fails, the saga must trigger compensating transactions. Publish cancel hotel booking event, publish cancel flight booking event. Why it's useful. Sagas manage eventual consistency across multiple services without relying on traditional, complex, and blocking two-phase commit distributed transactions. They allow long-running business processes to complete reliably, even if individual services encounter temporary issues. 5. Event stream processing/complex event processing, SEP, finding patterns in the flow. Sometimes, it's not enough to react to individual events. Instead, you need to react to patterns of events or aggregates of events occurring over time. What it is. This pattern involves continuous processing of event streams to identify patterns, correlations, trends, or anomalies. Specialized stream processing engines continuously analyze incoming events, looking for predefined sequences, thresholds, or aggregations, and then trigger actions or emit new, complex events when patterns are detected. Analogy: imagine a security guard monitoring multiple CCTV feeds. They're not just reacting to a single door opening an event. They're looking for a sequence of events. Person enters, goes to a restricted area, then attempts to open a safe, which, in combination, represents a suspicious, complex event that triggers an alarm. Similarly, a fraud detection system might look for multiple small transactions on a new card within a short period from different geographies. Why it's useful. Enables real-time analytics, dashboards, fraud detection, anomaly alerting, and dynamic pricing or personalization based on immediate user behavior. It transforms raw events into actionable business insights. 6. Dead letter queues, DLQ, the safety net for unprocessed events. Even with the best design, some events may fail to be processed successfully by a consumer, perhaps due to a bug, a malformed message, or an external system being unavailable. What it is? A DLQ is a specialized queue where events are automatically routed if they cannot be processed after a configured number of retries, or if they are explicitly rejected by a consumer. They act as a catch-all for problematic messages. Analogy: think of a post office's return to sender or undeliverable mail department. When a letter can't be delivered to the intended recipient and multiple attempts fail, it's sent to a special department for investigation or return. Why it's useful: prevents poison messages, events that continuously fail from clogging up the main processing queues and blocking other legitimate events. It provides a dedicated place to inspect failed events, diagnose the root cause, fix it, and then potentially requeue the events for reprocessing, preventing data loss and improving system robustness. These patterns are not mutually exclusive. They are often used in combination to build sophisticated and resilient event-driven systems. Understanding when and how to apply each one is key to mastering EDA. With these building blocks in your toolkit, you are now better equipped to move from theoretical understanding to practical application. In the next chapter, we will shift our focus to the vital technologies that turn these patterns into reality, powering the flow of events in modern systems. Chapter 6, the toolset, technologies powering your event stream. In the preceding chapters, we've outlined the foundational concepts, established a precise vocabulary, explained the compelling advantages of event-driven architecture, and even explored the common patterns that help us structure event flows. Now, it's time to bridge the gap between theory and practice. None of these advantages would be realized without the robust technological tools that power the event streams, manage their delivery, and enable services to interact seamlessly. Selecting the right technology for your event-driven system is a critical decision. The landscape is rich and diverse, featuring everything from mature, enterprise-grade platforms to cutting-edge cloud services. While we won't dive into specific vendor-level configuration details, understanding the main types of technologies and their typical roles will equip you to make informed choices. The core of any event-driven system relies on a reliable event broker. This intermediary is responsible for receiving events from producers and delivering them to consumers. Beyond the broker, other types of technologies aid in processing, storing, and visualizing the event flow. Let's explore the key categories of technologies that form the backbone of modern EDA implementations. 1. Event brokers/message queues/streaming platforms. These are the indispensable central hubs for events. They manage the publish-subscribe mechanism, ensure reliable delivery, and often provide persistence for events. Traditional message queues. Concept: focus on point-to-point delivery and durable queuing. Messages are typically consumed by one or a competing group of consumers and then removed from the queue. They often support various messaging patterns beyond pure publish-subscribe. Examples: RabbitMQ, a popular open-source message broker that implements the Advanced Message Queuing Protocol, AMQP. It's known for its flexibility, mature feature set, and support for complex routing scenarios using exchanges and bindings. Great for traditional queuing needs and some pub-sub scenarios. ActiveMQ, another long-standing open-source message broker from Apache, supporting a variety of messaging protocols. Cloud-managed queues, e.g., AWS SQS, Azure Service Bus, Google Cloud PubSub. These are fully managed services that abstract away the operational burden of running your own message broker. They offer high scalability, reliability, and integration with other cloud services. Google Cloud PubSub is noteworthy for blending traditional messaging with true streaming capabilities, making it a versatile choice. Best for tasks requiring reliable one-to-one or one-to-many delivery, worker queue patterns, and ensuring messages are processed even if consumers are temporarily offline. Distributed streaming platforms, event streaming platforms. Concept: built for high-throughput, fault-tolerant, real-time streams of events. Unlike traditional queues, events are typically appended to an immutable log, a topic, and not removed after consumption. Multiple consumers can read from the same topic at their own pace, and events can often be replayed from any point in time. This enables event sourcing and complex stream processing. Examples: Apache Kafka, the undisputed leader in this space. Kafka is an incredibly powerful, highly scalable, and fault-tolerant distributed streaming platform. It's designed for handling massive volumes of real-time data feeds and is the backbone of many large-scale event-driven systems. Its concept of immutable, partitioned logs makes it ideal for event sourcing and stream processing. Apache Pulsar. A newer challenger to Kafka, Pulsar offers an interesting architecture that separates storage from computation, brokers, and bookies, providing flexible scalability and native support for both queuing and streaming semantics. Redpanda, a Kafka API-compatible streaming platform written in C++. It aims to offer better performance and simpler operations than traditional Kafka by optimizing for modern hardware. Cloud-managed streaming services, e.g., AWS Kinesis, Azure Event Hubs, Confluent Cloud. Cloud providers offer managed services that leverage Apache Kafka or Kinesis-like capabilities, reducing the operational burden. Best for high-volume event ingestion, real-time data pipelines, log aggregation, event sourcing, and applications needing to process continuous streams of data. 2. Serialization formats. Events are essentially data, and that data needs to be structured and encoded for efficient transmission and storage. JSON, JavaScript Object Notation. Concept: human-readable, widely supported, and flexible data interchange format. Pros: easy to read, debug, and work within almost any programming language. No need for predefined schemas. Cons: can be verbose, leading to larger message sizes compared to binary formats. Lacks strong schema enforcement, making schema evolution more challenging without external governance. Avro concept: a data serialization system that relies on schemas. Both the producer and consumer share a schema that defines the structure of the data. The data itself is encoded in a compact, efficient binary format. Pros: very compact message size, strong schema validation, excellent support for schema evolution, adding fields, providing defaults. Makes it easier to handle different versions of events. Cons: less human-readable, requires schema management, often via a schema registry. Protobuf protocol buffers. Concept: Google's language-neutral, platform-neutral, extensible mechanism for serializing structured data. You define your data structure in a proto file, and a compiler generates code for various languages to serialize/deserialize your data. Pros: very compact and efficient, good performance, strong schema definition. Cons: not human-readable, requires code generation. 3 stream processing frameworks. Once events are flowing, you often need to process them in real-time filtering, transforming, aggregating, or joining them to derive new insights or trigger actions. Complex event processing. Apache Flink, a powerful open-source stream processing engine capable of high-throughput and low-latency processing, supporting real-time analytics, event-driven applications, and ETL. Apache Spark Streaming or Structured Streaming, part of the broader Apache Spark ecosystem. While Spark is primarily known for batch processing, its streaming modules allow for processing data in small batches or near real-time. Kafka Streams, a client library for Apache Kafka that allows you to build stream processing applications directly within your services. It's lightweight, doesn't require a separate cluster, and is ideal for microservices that need to react to and transform Kafka streams. Specialized cloud services, e.g., AWS Kinesis Data Analytics, Azure Stream Analytics, Google Cloud Dataflow. Fully managed services that provide powerful capabilities for real-time stream processing without needing to manage underlying infrastructure. 4 data stores and query layers. While events are the source of truth, systems often need materialized views of this data for efficient querying and display. CQRS is heavily reliant on these different data stores. Traditional relational databases, e.g., PostgreSQL, MySQL. still very much relevant for storing materialized views derived from events, especially if strong transactional consistency is needed for specific read models. NoSQL databases, e.g., MongoDB, Cassandra, Redis, Elasticsearch, often used for specific read models or for storing event data itself. Their flexible schemas and ability to scale horizontally make them suitable for diverse data access patterns. Elasticsearch, excellent for search-oriented read models and for indexing event data for analytical purposes. Redis, fast in-memory data store often used for caching materialized views or for very high-performance read access patterns. Graph databases, e.g., Neo4j, AWS Neptune, useful for read models where relationships between entities are central to the query, typically built by processing events that describe these relationships. Data warehouses/lakehouses, e.g., Snowflake, Databricks, Redshift. Events can be ingested into these systems for long-term storage and complex analytical queries, often aggregated into data models for business intelligence. 5. Monitoring and observability tools. In a distributed, asynchronous event-driven system, traditional debugging tools fall short. You need to understand the flow across services. Distributed tracing, e.g., Jaeger, Zipkin, OpenTelemetry. Tools that allow you to trace the full lifecycle of a transaction as it hops across multiple services and potentially multiple event hops. They provide visibility into latency, bottlenecks, and errors. Metric collection, e.g., Prometheus, Grafana, Datadog, for collecting and visualizing key metrics like event throughput, consumer lag, error rates, and resource utilization of event brokers and services. Log aggregation, e.g., Elk Stack, Elasticsearch, Logstash, Kibana. Splunk, Datadog logs. Consolidating logs from all services into a central searchable repository is crucial for debugging and operational insights. The sheer number of options can be daunting, but the choice often comes down to balancing factors like your existing technology stack, team expertise, scalability requirements, operational budget, and the specific needs of your domain. Most production-grade EDA implementations will typically involve a combination of these technologies, carefully selected and integrated to create a robust and efficient event stream. In the next chapter, we will shift from discussing the individual components to the holistic process of designing a robust event ecosystem, focusing on architectural principles and practical considerations for bringing these technologies together effectively. Designing an event-driven system is less about simply picking the right technologies and more about truly embracing a new mindset. It requires careful thought, discipline, and a deep understanding of the business domain. The patterns and technologies we discussed in previous chapters are the tools, but effective design provides the blueprint for how to use them to build a thriving event ecosystem. This chapter delves into the guiding principles for successful EDA design, helping you navigate the complexities and maximize the benefits we've explored. 1. Events as first-class citizens. Focus on what happened, not how to act. The most fundamental design principle in EDA is to correctly identify and define your events. An event declares a fact about something that has already occurred in the business domain. Purity of events. Events should be immutable, past-tense representations of a factual occurrence. Avoid naming events with verbs that imply a command, process order, or a query, get customer details. Instead, focus on the state change, order placed, customer activated, inventory adjusted. Granularity, how detailed should an event be? Start with events that represent significant business changes. For example, instead of a customer address updated event for every single field change, an event like customer profile updated might suffice, containing key facts. If the downstream consumers are interested in the broader profile change rather than atomic address line updates. The goal is to capture enough information relevant to downstream consumers without making the event overly chatty or too large. If new consumers emerge with different granular needs, you can always derive more specific events from broader ones, or even have them consume the same event and pull more details. Minimal data. Events should typically carry only the essential data required to describe the occurrence and enable interested consumers to find associated details. For instance, an order-placed event might contain the order ID, customer ID, timestamp, and total price, but not necessarily every line item detail. Consumers needing line items would then use the order ID to query a dedicated order service. This reduces event size and coupling. 2. Embrace bounded contexts and domain-driven design. Event-driven architecture thrives when implemented within the framework of bounded contexts, a core concept from domain-driven design, DDD. Clear ownership. Each bounded context, which typically maps to a microservice or a logical service boundary, should own its events. It is the authoritative source for any events originating within its domain. For example, a customer management context owns customer-registered and customer-updated events, while an order management context owns order-placed and order-shipped events. Event as contract. Events flowing between bounded contexts define their integration contracts. Changes to these public events must be carefully managed, see schema governance below, because they impact other contexts. Transformation, not mutation. When an event from one context is consumed by another, the consuming context might transform or interpret that event in its own domain language. It doesn't modify the original event. Rather, it uses it to create new facts or trigger actions within its own boundaries. 3. Design for resilience and fault tolerance from day one. Given the asynchronous and distributed nature of EDA, anticipating and handling failures is paramount. Idempotency. As highlighted in Chapter 4, consumer operations must be idempotent. This means processing the same event multiple times should produce the same result as processing it just once. Achieve this by tracking processed events. Store the unique event ID in your consumer's database after processing. Before processing, check if the ID already exists. Designing idempotent operations. For operations like set, assign a value, rather than increment, add to a value where possible. External transaction IDS. Using a unique ID provided by the producer for tracking entire business transactions. Retries and backoff. Design consumers to gracefully handle transient failures, network glitches, temporary unavailability of a dependent service. Implement retry mechanisms with exponential backoff, waiting progressively longer between retries to avoid overwhelming the failing service. Dead letter queues, DLQ. Utilize your event broker's DLQ feature for events that cannot be processed after a maximum number of retries. This moves poison messages out of the main queue, allowing other events to be processed, and provides a designated spot for manual inspection and troubleshooting. Backpressure mechanisms. Consumers should have a way to signal if they are overwhelmed and cannot process events at the current rate. This allows producers or the broker to temporarily slow down message delivery, preventing system collapse. 4. Schema governance is paramount. Events are shared contracts. Without proper discipline in managing their structure, changes can ripple through the system disastrously. Define clear schemas. Use schema definition languages like Avro IDL, Protobuf IDL, or JSON schema to formally specify the structure and types of data within each event. Schema registries. For Kafka and similar systems, a schema registry is invaluable. It centralizes event schemas, ensuring producers and consumers use compatible versions. It enforces schema evolution rules, e.g., backward and forward compatibility. Versioning strategy. Plan for how events will evolve. Backward compatible changes, additive. Adding new optional fields is usually safe, as older consumers can ignore them. Backward incompatible changes, breaking. Renaming, removing, or changing the type of existing fields requires careful coordination, and often involves creating a new version of the event order, placed v2, and potentially running old and new consumers in parallel for a migration period. 5. Establish a robust observability strategy. Debugging and understanding the behavior of asynchronous, distributed systems is inherently challenging. Proactive observability is not an afterthought, it's a design requirement. Distributed tracing. Implement a distributed tracing solution, e.g., OpenTelemetry, Jaeger. Each service should propagate a correlation ID across events. This allows you to reconstruct the entire activity flow, seeing how an event traverses multiple services and identify bottlenecks or failures. Structured logging. Ensure all services emit structured logs, e.g. JSON format, that include relevant context trace IDs, event IDs, service names, timestamps. This makes logs searchable, filterable, and aggregatable in centralized logging systems. Meaningful metrics. Collect and expose metrics about your event processing, event throughput, events published consumed per second. Consumer lag. How far behind a consumer is from the latest event in a stream, critical for identifying processing backlogs. Error rates, number of failed event processes. Retry counts, how many times an event was retried. Resource utilization, CPU, memory, network for services and brokers. 6. Think eventual consistency, plan for reconciliation. Accept the reality of eventual consistency. Your system will not always be perfectly synchronized at every millisecond. Design for tolerance. Identify where strict immediate consistency is truly non-negotiable, rarely needed at a global level, and where eventual consistency is acceptable. Often, humans can tolerate small delays. Reconciliation mechanisms. For critical data that must eventually converge, design mechanisms to detect and resolve inconsistencies. This might involve periodic batch processes that compare data across services and reconcile discrepancies, or re-emitting events to trigger reprocessing. UI considerations. Inform the user about the eventual nature of certain operations. For instance, your order has been placed. Payment confirmation will be sent shortly. 7. Focus on business capabilities, not just technical components. Ultimately, your event-driven system exists to serve business needs. Event storming. This collaborative workshop technique, bringing together business and technical stakeholders, is an excellent way to discover events, commands, and aggregates directly from business processes. It helps align technical design with real-world business flows. Define business value. For every event and every service that processes it, ask why. What business problem does this solve? How does it contribute to the overall value proposition? 8. Start small, iterate, and learn. Don't attempt a big bang overhaul of your entire architecture. Pilot project. Begin with a well-defined, contained problem that can benefit from EDA. This allows your team to gain experience, establish processes, and validate technologies without undue risk to core business operations. Iterative rollout. Gradually introduce new event-driven components, integrating them with existing systems. This allows for learning and adaptation. Continuous improvement. EDA is an ongoing journey. Regularly review your design principles, technologies, and operational practices as your understanding deepens and your system evolves. Successful event-driven architecture is a blend of technical expertise and thoughtful, domain-driven design. By adhering to these principles, you can build systems that are not only powerful and efficient, but also adaptable, allowing your organization to respond rapidly to changing market conditions and continue innovating. In the next chapter, we'll move from design to execution, exploring the practical steps of implementing and testing these complex event-driven systems. Chapter 8, From Idea to Reality, Implementing and Testing Event-Driven Systems. We've covered the what, why, benefits, challenges, patterns, and design principles of event-driven architecture. Now it's time to move into the practical realm. How do you actually build and test an event-driven system? This chapter will guide you through the concrete steps, considerations, and best practices for bringing your event-driven vision to life. Implementing EDA is not just about writing code. It's about configuring infrastructure, setting up development workflows, and fundamentally rethinking how you approach testing in a distributed, asynchronous environment. 1. Setting up your development environment. Before you write a single line of code, establishing an efficient development environment is crucial. Local event broker. For development and immediate testing, running a lightweight version of your chosen event broker, e.g., Kafka, RabbitMQ, locally on developer machines is highly recommended. Tools like Docker or Vagrant make this easy to containerize and spin up. This allows developers to work without constant network dependencies. Containerization, Docker/Kubernetes. Use containerization for your services. It offers consistent environments from development to production, simplifies dependency management, and streamlines deployment. Kubernetes has become the de facto standard for orchestrating containerized applications, making it an excellent choice for deploying event-driven microservices at scale. Code generation for schemas. If you're using schema-defined formats like Avro or Protobuf, integrate code generation into your build process. This ensures that the data structures for your events are automatically created in your chosen programming language, reducing manual errors and ensuring type safety. Centralized schema registry access. Developers need easy access to the schema registry, if used to register new schemas and retrieve existing ones, particularly when writing producers or consumers. 2. Implementing event producers, sources. The producer's main responsibility is to correctly identify and emit events when significant state changes occur. Identify event triggers. Pinpoint the exact moments in your business logic when an event should be generated. This is often after a successful transaction or a state transition. Atomic operations. Ensure that the emission of an event is tightly coupled with the change in the producer's internal state. Ideally, the event publication should be part of the same transaction as the state change to guarantee atomicity. This is known as the transactional outbox pattern. Instead of directly publishing the event, store it in an outbox table within the same database transaction as your main business data. A separate background process then picks up these events from the outbox and publishes them to the event broker. This guarantees that either both the state change and event publication succeed, or both fail, preventing data inconsistencies. Include essential metadata. Events should carry not just the data about what happened, but also essential metadata for correlation and observability. Event ID, a unique identifier for the event. Timestamp, when the event occurred. Source producer ID, which service component emitted the event. Correlation ID trace ID, generated at the start of a business transaction and propagated through all subsequent events and commands in that transaction. Crucial for distributed tracing. Version, the schema version of the event. 3. Implementing event consumers, listeners. Consumers are where the business logic that reacts to events resides. Subscribing to topics queues. Configure consumers to subscribe to the relevant topics or queues from the event broker. Message consumption loop. Consumers typically run in a continuous loop, fetching events from the broker. Idempotency is key. As discussed in Chapter 4 and 7, ensure your consumer logic is idempotent. This protection against duplicate event processing is non-negotiable. Implement logic to check if a particular event, identified by its unique ID, has already been processed within the consumer's context. Error handling and retries. Robust error handling is paramount. Transient errors. For temporary issues, e.g., database connection timeout, implement automatic retries with exponential backoff. Poison messages. For persistent errors, e.g., invalid event format, business logic error that cannot be resolved automatically, send the event to a dead letter queue, DLQ, after a defined number of retries. Alert operators about DLQ messages for manual inspection. Acknowledge messages. Once an event is successfully processed and its side effects are complete, e.g., database updated, explicitly acknowledge its processing to the event broker. This tells the broker it can consider the message delivered and potentially remove it from the queue or advance the consumer's offset in a stream. Failing to acknowledge can lead to reprocessing the same message repeatedly upon consumer restart. Separate concerns. Keep consumer logic focused on reacting to the event and performing its specific business function. Avoid embedding complex business rules from other domains within a consumer. 4. Testing strategies for event-driven systems. Testing EDA presents unique challenges due to its distributed and asynchronous nature. Traditional unit and integration tests are still valuable, but new types of tests are essential. Unit tests test individual components, producers, consumers, business logic functions in isolation, mock out external dependencies and the event broker. Integration tests, service level. Test how a producer interacts with the event broker. Can it publish correctly? And how a consumer interacts with the broker. can it subscribe and process events, as well as its internal dependencies, e.g., database. Component tests spin up a single service and a real local event broker. Test the entire flow through that service, from event ingestion to event emission. End-to-end, E2E/system tests, these are critical. They involve deploying a subset or all of your event-driven services, along with your actual event brokers, and simulating real-world scenarios. Challenge with asynchronicity. Waiting for an event to propagate and be processed by multiple services asynchronously is difficult. E2E tests often require sophisticated setup to assert outcomes. Test data setup. Orchestrate test data across all services involved in a flow. Assertions on final state. Instead of asserting on intermediate steps, often you assert on the final state in a downstream system, e.g., check a database, verify an external API call was made. Observability in tests. Use distributed tracing and logging insights during E2E tests to understand the flow and pinpoint issues. Test containers. Libraries like test containers can be invaluable for spinning up real event brokers and databases in your test environment programmatically. Contract tests, consumer-driven contracts. Ensure that the contracts, event schemas between producers and consumers remain compatible. A consumer defines what it expects from an event, and this contract is then verified against what the producer actually produces. This catches breaking changes early. Chaos engineering, advanced. Intentionally inject failures, e.g., kill a consumer, inject network latency into your system to observe how it behaves under duress. This helps validate your resilience mechanisms. 5. Continuous integration/continuous delivery, CI/CD. Automating your build, test, and deployment processes is fundamental for managing the complexity of multiple, independently deployable services. Automated testing. All the test types mentioned above should be part of your automated CI pipeline. Independent deployments. Each service should be able to be built, tested, and deployed independently of other services, reducing deployment risk. Blue, green, or canary deployments. For critical services, use deployment strategies that allow new versions to be rolled out gradually or alongside the old one, enabling rapid rollback if issues arise. Environment parity. Strive for environments, development, staging, production, that are as similar as possible to minimize works on my machine issues. 6. Documentation and knowledge sharing. Given the distributed nature, clear documentation of your events, services, and their interactions is paramount. Event catalog. Maintain a centralized, up-to-date catalog of all events in your system, including their schemas, purpose, and key producers' consumers. This serves as a vital resource for new hires and for understanding system boundaries. Service documentation. Document each service's responsibilities, the events it produces, and the events it consumes. Runbooks and operational guides. Clear instructions for how to operate, monitor, and troubleshoot your event-driven services in production. Bringing an event-driven system to life involves a systematic approach, from careful environment setup and meticulous implementation of producers and consumers to sophisticated testing and robust deployment practices. It's an investment that pays off in system agility, scalability, and resilience, but only if executed with discipline. In the next chapter, we will discuss how to keep the flow steady once your event-driven architecture is in production, focusing on operation, monitoring, and evolution. Chapter 9, Keeping the Flow Steady. Operating and evolving your event-driven architecture. The challenging but rewarding journey of an event-driven architecture doesn't end with its successful deployment. In many ways, that's just the beginning. The operational phase of an EDA is where its true resilience, scalability, and agility are continuously tested and realized. Managing the ongoing flow of events, ensuring system health, responding to incidents, and adapting to ever-changing business needs requires a dedicated focus on operations and a mindset of continuous evolution. This chapter explores the critical aspects of operating a live event-driven system and how to ensure it remains a dynamic, valuable asset rather than becoming a brittle liability. 1. Relentless observability. Knowing your system's pulse. In a distributed, asynchronous environment, failures don't always manifest as a single, obvious error message. They can present as slower processing, accumulating backlogs, or subtle data discrepancies. This makes robust observability paramount. Centralized logging. All services and the event broker itself must emit structured logs to a centralized logging platform. This allows for quick searching, filtering, and analysis across the entire system. Logs should include correlation IDs, from distributed tracing, to reconstruct request flows, service names, event IDs, and timestamps. Comprehensive metrics. Gather operational metrics from every component. Event broker metrics. Event throughput messages per second, message size, partition health, disk usage, network I/O, and consumer group health. Service metrics. CPU memory utilization, error rates, latency of internal operations, and thread pool usage. Application-specific metrics. Business-level metrics derived from events such as orders placed per minute, users registered per hour, or failed payments. Consumer lag monitoring. This is a crucial metric for streaming platforms. Consumer lag indicates how far behind a consumer group is from the latest event in a topic. High or increasing lag suggests a consumer is struggling to keep up with the incoming event rate, potentially leading to processing delays or data consistency issues. Distributed tracing. As discussed in Chapter 7, distributed tracing is invaluable. It allows you to visualize the entire path an event takes through your system, from its origin to its ultimate consumption and any subsequent events it triggers. This is essential for debugging complex, multi-service interactions and latency issues. Alerting and dashboards. Transform your metrics and logs into actionable insights on real-time dashboards. Set up automated alerts for critical thresholds, e.g., high consumer lag, increased error rates, full dead letter queues to notify operations teams proactively. 2. Seamless operations. Keeping the event broker and services healthy. The event broker is the heart of your EDA. Its continuous, healthy operation is vital. Broker management. Whether self-hosting, e.g., Kafka clusters, RabbitMQ instances, or using managed cloud services, ensure regular maintenance. Scaling. Be prepared to scale the broker infrastructure up or down based on event volume and throughput requirements. Upgrades and patches. Apply security patches and version upgrades promptly. For self-managed systems, plan these carefully to minimize downtime. Replication and high availability. Configure the broker for high availability, e.g., Kafka's replication factor, to ensure no single point of failure and data durability. Backups. For event streams you wish to retain for long periods, ensure robust backup and archival strategies, e.g., offloading Kafka logs to object storage. Consumer group management. Monitor consumer group rebalances, which can indicate issues. Ensure consumers are correctly configured to join groups and process partitions efficiently. Error handling in production. Dead letter queues, DLQs. Continuously monitor your DLQs. Events landing there require investigation. Set up automated processes to alert on new messages in, manual intervention and replay. Sometimes, human intervention is needed to fix a problem and reprocess events, e.g., reprocessing messages from a DLQ after a bug fix, or even to replay historical events from the mainstream for specific recovery or reconciliation scenarios. Tools and processes for safe event replay are essential. Disaster recovery, Doctor. Plan for outages of entire data centers or regions. This involves replicating event streams across geographies and having strategies for failover and failback. 3. Fortifying the flow. Security and EDA. Security cannot be an afterthought in any modern architecture, especially one that handles potentially sensitive data and relies on interconnected services. Authentication and authorization. Secure access to the event broker. Producers should only be authorized to publish to specific topics, and consumers only to subscribe to specific topics. Use strong authentication mechanisms, e.g., Kerberos for Kafka TLS client certificates. Encryption. In transit, encrypt data as it moves between producers, the broker, and consumers, e.g., using TLS SSL. At rest, encrypt data stored by the event broker, e.g., Kafka logs on disk, and by your databases. Data masking and sanitization. Events should ideally not contain highly sensitive personal identifiable information, PII, or financial data directly. Instead, they should include references, e.g., userid, orderid, that can be used by authorized services to retrieve the full data from secure, primary data stores. If sensitive data must be in events, ensure it's encrypted or masked. Least privilege principle. Grant producers and consumers only the minimum necessary permissions to perform their functions. 4. Adapting to change. Evolving your architecture. One of EDA's promised benefits is agility, but achieving it requires a disciplined approach to change. Schema evolution management. This is paramount. As discussed in Chapter 7, carefully managing event schema changes using versioning and a schema registry is key to avoiding breaking existing consumers. Regularly review and curate your event schemas. Adding new services consumers. The beauty of EDA. Adding new functionality often means simply writing a new consumer that subscribes to existing events. This allows for rapid iteration and deployment of new business capabilities without impacting existing services. Deprecating old events or services. Eventually, some events might become redundant or services might be retired. Establish clear deprecation policies. Communicate changes to all teams. For events, this might involve a phased deprecation period where old events are still published, but new producers are encouraged to use updated versions. Blue, green, and canary deployments. Utilize modern deployment strategies. Blue-green deployments involve running two identical production environments, blue for the current version, green for the new. Traffic is switched to green only after it's validated. Canary deployments involve gradually routing a small percentage of traffic to a new version, monitoring its performance, and then slowly increasing traffic until it handles 100% of the load. These reduce risk when deploying updates to event-driven services. Continuous improvement through feedback loops. Regularly review incident reports, performance metrics, and team feedback. Conduct postmortems for major incidents to identify root causes and implement preventative measures. This iterative improvement process is crucial for maturing your EDA. 5. Organizational alignment. The human element. Ultimately, the success of an EDA in operation and evolution hinges on collaboration and shared understanding across teams. Shared ownership. Components of an EDA are interdependent through events. Fostering a sense of shared ownership and collaboration among teams is vital. Documentation and standardization. Maintain a living event catalog, API documentation for event contracts, and standardized guidelines for event design, naming conventions, and best practices. Training and evangelism. Ensure that new team members are onboarded quickly and effectively into the event-driven mindset. Continue to advocate for and educate about the principles of EDA. Operating and evolving an event-driven architecture is an ongoing commitment to a dynamic, distributed paradigm. It demands robust tooling, vigilant monitoring, and a proactive, collaborative culture. By mastering these operational aspects, organizations can fully leverage the promises of agility and resilience, ensuring their digital systems remain responsive and robust in an ever-changing world. With these practical considerations in mind, we can now turn our eyes to the future horizon of event-driven systems and beyond in our final chapter. Chapter 10, The Horizon Ahead, the Future of Event-Driven Architectures and Beyond. We've journeyed through the intricate landscape of event-driven architecture, from its fundamental concepts and profound benefits to its inherent challenges, essential patterns, enabling technologies, and the critical aspects of implementation and operation. As we conclude, it's clear that EDA is not merely a passing trend, but a foundational paradigm increasingly central to modern software development. But where is EDA headed, and what does the broader future of distributed systems hold? The horizon ahead for event-driven architectures is one of continued maturation, deeper integration with emerging technological trends, and a broadening of its application across diverse industries. 1. Hyperpersonalization and real-time experiences. The demand for hyper-personalized, real-time user experiences continues to grow. From instant recommendations on e-commerce sites to dynamic pricing in ride-sharing apps and personalized news feeds, events are the lifeblood. As machine learning, ML, becomes more pervasive, real-time event streams will increasingly feed ML models, allowing for immediate inference and adaptation based on live user behavior. Imagine a system where a single-click event can immediately alter a user's promotional offers or adjust the content they see. This requires lightning-fast, event-driven processing at the edge and in the cloud. 2. Event-driven micro-frontends. While EDA has largely focused on backend services, its principles are extending to the front end. Micro-frontends, where large web applications are broken into smaller, independently deployable parts, can leverage events to communicate without tight coupling. A user action in one micro-frontend, e.g., clicking Add to Cart, could emit an event that other micro-frontends, e.g., a mini cart display or a recommendation widget, subscribe to and react to dynamically. This extends the benefits of agility and scalability to the user interface layer, enabling more responsive and modular web experiences. 3. Serverless and FaaS, function as a service, integration. Serverless computing and function-as-a-service platforms, like AWS Lambda, Azure Functions, Google Cloud Functions, are inherently event-driven. They are designed to execute code in response to specific events, e.g., a file uploaded to storage, a message arriving on a queue, an HTTP request. This symbiotic relationship is set to deepen, making it even easier to build reactive, scalable microservices without managing any underlying infrastructure. The future will see more sophisticated event triggers and deeper integration with event streaming platforms, enabling complex serverless workflows. 4. Event mesh, the next evolution of event brokers. As organizations grow and decentralize, they often end up with multiple event brokers and messaging systems spread across different clouds, regions, or even hybrid environments. An event mesh is an architectural layer that connects disparate event brokers, allowing events to flow seamlessly and securely across different environments and technologies. It's like an intelligent network for events, enabling universal event connectivity. This will simplify complex inter-application communication, data synchronization, and enable truly global, interconnected systems, breaking down data silos that still exist. 5. Data mesh and event-driven data products. The data mesh paradigm, which advocates for decentralizing data ownership and treating data as a product, aligns perfectly with EDA. Data products can be exposed as event streams, providing domain-oriented, real-time access to valuable information. Instead of relying solely on batch ETL, extract, transform, load processes to move data into central data warehouses, organizations can consume real-time event streams from various domains to build continuously updated data products, fostering faster analytics and more immediate business decisions. 6. Enhanced observability and automation. As EDAs grow in complexity, the need for advanced observability tools will intensify. We'll see further innovation in automated anomaly detection, predictive analytics for system health, and self-healing capabilities. AI-powered operations, AIOps, will play a larger role in analyzing event streams and operational metrics to automatically identify, diagnose, and even remediate issues before they impact users. The goal is to move from reactive troubleshooting to proactive, intelligent system management. 7. Event-driven security. Security operations are increasingly looking to leverage events. By processing security-relevant events, e.g., login attempts, access failures, data modifications, in real time as a stream, organizations can detect and respond to threats faster. This includes using event stream processing for real-time fraud detection, intrusion detection, and compliance monitoring, fundamentally shifting security from static analysis to dynamic, reactive defense. 8. Web3 and decentralized event streams. Looking further ahead, the intersection of EDA with decentralized technologies like blockchain, Web3, is an emerging area. Smart contracts on a blockchain can emit events, establishing an immutable, publicly verifiable log of activities. This could lead to genuinely decentralized event streams, enabling new forms of transparent and trustless collaboration across organizations, particularly in areas like supply chain traceability, digital identity, and tokenized assets. The enduring promise of the event. Despite these futuristic visions, the core philosophy of event-driven architecture remains constant, reacting to what has happened rather than constantly asking, "What should I do now?" This seemingly simple shift fundamentally alters how we design, build, and operate software. It moves us away from brittle, centralized control to agile, decentralized coordination. Mastering EDA requires a journey of continuous learning. It demands a different way of thinking about data, communication, and system boundaries. It pushes us to embrace eventual consistency, design for failure, and foreground observability. While the tools and patterns will continue to evolve, the underlying principles of loose coupling, asynchronicity, and building systems around immutable facts will remain cornerstones of robust, scalable, and adaptable software. As our digital world becomes even more interconnected, real-time, and distributed, the ability to effectively manage and react to the pulse of events will not just be a competitive advantage. It will be a prerequisite for survival and innovation. The event-driven blueprint is not just for today's systems, but for the complex, dynamic systems of tomorrow. Go forth and embrace the flow.